Okay, so if you live in Calgary, Alberta, or just in Alberta in general, and you're in Chem 30, your diploma is on Monday. So I just wanted to quickly go over some of those concepts that you need to know for every unit that could come up. So the first little bit is just talking about those key concepts. So what's in thermochem, so knowing about enthalpy of formation, energy diagrams, your enthalpy of reaction, activation energy. All of this is definitely going to come up, but we can be a little bit more specific. So for instance, for this first part, when it's talking about recalling the application of Q equals MC delta T. If that does come up, we want to remember that this formula is only if you're heating and cooling a substance. It's not a chemical reaction. So if you put a piece of metal and you're heating it up or cooling it down, we can calculate the Q of that or the C value. We also want to know that all energy is originating from the sun. We want to know the difference between enthalpy and molar enthalpy for reactions. So enthalpy would be for the whole reaction. Molar enthalpy is when you would divide by the amount of moles of the species you're looking at. We want to be able to write out balanced equations. We should be good at that. But now we're going to include enthalpy. So your delta H is either going to be within that equation or on the outside. And if it is, then that's how we also show that we know how to communicate delta H. This other formula that we would be using here would be NH equals delta H, and that is when we're looking for the delta H of heat being absorbed or released based on the amount of moles within the reaction. So when you're using this formula, you want to remember that this H here is the delta H from the reaction. So it gets confusing because it will look the same. Then just moving on from here, predicting the enthalpy change using standard enthalpies of formation. This, in my very short way I write it out, is delta H is products minus reactants. So you would use page 4 or 5 of your data booklet, and this is Hess's law short. Number 7 is Hess's law long, when you have a series of reaction to get to your target. Number 8, using calorimetry, that would be the formula NH equals negative MC delta T. NH would be your side that talks about the reaction, and the negative MC delta T is about what's happening with water. Now with calorimetry, you also want to know your 3 assumptions about your system. You'd also want to know bomb calorimetry because that can come up. It's just not as common as regular calorimetry questions. Looking at number 9, this one tells you that you can identify that liquid water and carbon dioxide are reactants in photosynthesis and products in cellular respiration. So I often mention that know these reactions because sometimes a diploma can be nice to you and write it out. Other times it doesn't, and you have to be able to write it out and recall it. The next part is just talking about that open system and knowing the difference. And I did a video about this recently. If you have water in an open system, it has a gas state. If you're in a closed system, it's going to be the liquid state. Looking at number 10, being able to say if you're endo or exothermic, and that includes for photosynthesis, which would be endo, cellular respiration, which would be exo, and combustion reactions, which is also exo. Now we're moving on to activation energy, knowing that if you did have your potential energy diagrams, that activation energy is always that hill you need to get over. It's from your reactants to the top. Then that's that energy barrier before the chemical reaction can occur. Number 12 here, being able to understand in chemical reactions, breaking and forming bonds and how that changes potential and kinetic energy. So if you break bonds, breaking of the bonds, you must put energy in. A bond's just not going to break on its own. So that's an endothermic reaction. Forming bonds would be exo. That's how heat is released. Potential energy is when you have a chemical reaction, and kinetic energy is just having that heating of cooling of particles. Looking at number 13, looking at labeling energy diagrams, this would be whether it's endo or exo. So if it was endothermic, we know that our graph would look like the one I just drew above. If it's exo, it's the other way, and being able to understand and add in activation energy. Moving on, I keep saying moving on, but there's just a lot here. We also want to know what catalysts do, and that enzymes is a special name for catalysts. And if you're in bio, that probably would make a little bit more sense. And how that it just creates a faster pathway for that energy to take place. So it lowers activation energy. Now, there are some specific examples here of how we also want to add in and have that understanding of fossil fuels, and knowing that if we want it to be efficient, we don't want to over pollute. We want to be able to use all of that energy in a useful way. The other part that can come up here is experimental design, as some of you have seen in questions. And that's usually when you're taking a look at a calorimetry experiment and you're changing the fuel used. Now, just going over it one more time, because variables can get a little bit confusing. If you have, say it's calorimetry, and you're manipulating a variable, your manipulated variable is probably going to be the type of fuel. That's the most common. Then your controlled variable could be the type of calorimeter, and so on. And then lastly, your responding is always what you're looking for. What are you measuring? And in calorimetry, you're always measuring for temperature. So that is our first one for thermochem, just those major concepts you need to know. And then of course you can try a bunch of questions, try as many old diploma questions as you can. The next one is electrical chem, so electrochem. And here we are looking at many things. We start by looking at those definitions regarding oxidation, reduction, all of that. And eventually we move it into cells and have that understanding of cells. And then we even move on to cell stoic. There's that term disproportionation you want to know, and a few others in here. So let's start going over this. So if you have oxidation, we know that you are losing electrons. Reduction, you are gaining. When you're figuring out what's undergoing oxidation or reduction, you always pick a reactant, right? So products help us see what's happening, but reactants are what undergo oxidation and reduction. So remember, if you're undergoing oxidation, think oil, and you would be a reducing agent. And if you are undergoing reduction, think rig, and you would be an oxidizing agent. You can also look at half reactions, and we definitely want to know that any redox reaction is always identified because you are transferring electrons. So I recently did another video where you can recognize redox reactions, and that's just assign your oxidation numbers and see if you have an OA and an RA. If you don't, you can still be a reaction, you're just not a redox reaction. Now, there's also this point number 5, comparing strengths. Here you're using your data booklet. So knowing that if you had your data booklet, which shows reduction, and that would be on page 7, that your OAs are on the left, your RAs are on the right. Your strongest OA is at the top, and as you go down, you get weaker. Your strongest RA is on the bottom right, and as you go up, you get stronger. You get weaker. So we have that, and then based on that, you could also predict and make a table and then interpret that table. So building redox tables. Then there's also parts that you'd have to balance in acidic conditions. So you want to know your rules for that. And as mentioned in class, or if you have an outdated textbook, there's also rules for basic conditions, but that is no longer in the curriculum. So you just need your acidic conditions rules if that comes up. Keep on going from here. I'm looking at number 8 now. Perform calculations to determine the substances involved in redox titrations. So for number 8, that's when you want to take a look at what's reacting and then compare it to the table. Pick your strongest OA, react it with your strongest RA. Once you set up and balance out your reaction, then you can do the stoic part, which is just like chemistry 20. So it's just like solution stoic. For question number 9, or not question, point number 9, now we're starting to look at voltaic and electrolytic cells, which would have an anode, a cathode. We have ions that travel through the salt bridge. We have electrolytes that allow those ions to move in solution. You have your external circuit, which allows your electrons to transfer, and all of that we'll move on from there. We want to know the difference between voltaic and electrolytic. So knowing that voltaic will take chemical energy and make electric energy, whereas electrolytic, you have to put in electricity to get out that chemical reaction. You do want to be able to write out your half reactions that occur at each electrode. So knowing that your anode is the site of oxidation, so that's where we're losing electrons, and you have your reducing agent will be your anode. Whereas your cathode is the site of reduction. So you're undergoing reduction, you're gaining electrons, but it's the ion in solution that is going to be your oxidizing agent. Moving on from there, number 12 is saying that your predictive reaction doesn't always occur. And this has to do with the chloride anomaly. And if you're looking at RAs, if you have the choice between chlorine and water, you pick chlorine even though water shows up first. I just need to move this up a little bit now. So looking now, if I keep going from here, where 13 says why standard electrical potentials has 0 for the hydrogen cell and how we can change it and how everything moves. Knowing spontaneity, so if your OA is above your RA, you have a spontaneous reaction. If your RA is above your OA, it is non-spontaneous. And this also has to do with your cell potentials. So if your cell potential is positive, you have a spontaneous reaction. If your cell potential is negative, it's non-spontaneous. And then lastly, you can use Faraday's law, which involves the formula moles of electrons equals your current times time in seconds divided by Faraday's constant. And that allows us to figure out how much mass is lost or gained in a electrolytic cell. The nice thing about this is you just need a half reaction to figure out. You don't need the whole thing. So whatever's being plated or losing or gaining mass, we just want that half reaction, and then you can apply this formula. So there's a little bit more here where it's starting to talk about corrosion. You do want to read over that. There's a lot of theory there about how you prevent corrosion and how you can have a sacrificial anode, which means you are protecting your cathode. There's many things here. Just make sure that when you are studying that you're also reading over corrosion, because oftentimes there would be one quick question on that if it does come up. I think that would be about it here. And then we can move on to organic. So with organic, it's really mainly those names. You want to be able to name all of the different type of compounds that we have learned. And then it moves on to the chemical reactions that we would get from organic reactions. And then lastly, knowing the difference between monomers and polymers and the theory behind those. So let's start to go over this. So starting to define organic. So here you want to know what's not organic. There is a list here. So just remembering those. Then going through how organic compounds are essentially everywhere and how to name it. So there's tons of information here. Usually if you can get through the first few lessons, you'll start to notice how often organic compounds and naming, how you have the basis and then you're just adding a little bit to it. So do you know how to name alkanes, alkenes, and alkynes? How we have to name a double or a triple bond, how we need to recognize that. There are formulas there, but you also know how to draw this out. Number 4 says identify compounds based on the hydroxyl group, meaning you have an alcohol, carboxyl group if you have a carboxylic acid, an ester link or a halogen if it's on there, and being able to name it from there. You also want to be able to identify isomers. So if you can break down a compound to have the same empirical formula, meaning the exact same amount of carbons, hydrogens, and whatever else might be there, it could be an isomer. So it's when you have exact same amount, they're just arranged differently. You do also want to know homologous series. So if you have a homologous series, it just means you're part of the same family and you're just getting bigger and bigger. So if I looked at alkanes, I could start with methane, then ethane and propane and so on. Those would be part of a series. And the same thing would be for alcohols and carboxylic acids. You also want to know how boiling points are affected. So knowing like our simple groups, like alkanes, alkenes, and alkynes, right? They have relatively low boiling points because they only have LDF forces. But as soon as you start to add on anything that is polar, like an alcohol, carboxylic acids with some lone pairs, your boiling point is going to start to get higher. Moving on. Describe, in general terms, physical and chemical process of fractional distillation. So just knowing how you're using boiling point to separate your hydrocarbons. Number 8 is going over your reactions. So knowing that if you have a simple addition, you are breaking a double bond. So you would have had a double bond present that needs to be broken, and we're adding to your original molecule. Substitution, you are just swapping places. You have one molecule and another molecule, and something within is going to swap to make 2 brand new molecules. Elimination, you are starting with one molecule, but you are eliminating off of that molecule, and you are going to form a double bond and one more molecule. Esterification is when you have that alcohol coming close to a carboxylic acid to form that ester and water, and combustion reactions are what you're used to. So don't overthink that one. Have your hydrocarbon, react it with oxygen. Products are always carbon dioxide and water. You want to be able to draw out or name depending what you're given. And then lastly, talking about polymers. So if you have a monomer and you want to make it a polymer, we know we can do that by 2 types of reactions, whether it's an addition reaction or a condensation reaction, meaning we're joining by water leaving the 2 molecules that come near each other and the rest link together. The other part that you want to remember with polymers is that they're special because they can act like a liquid on impact. So I think those are our main points. Just want to make sure I'm not forgetting anything here. Based on the rest here, it's a little bit repetitive, and that's okay. So this last one is about equilibrium and acid and base systems. So you do want to know the definition of equilibrium, what makes a system in equilibrium. You do want to know about Bronsted and Lowry. We want to know what happens when you reverse a reaction. We want to be able to draw and understand titration curves. We have Le Chat and how you can stress the system. Acid-base pairings, your equilibrium law expression, so calculating Kc or using Kc, how you know something is amphiprotic, meaning you can act like an acid or a base, what makes something a buffer, and then acid bases being in equilibrium, if you have an indicator, how you can tell. So just going over all of that in a few more details. So the first one, as mentioned, knowing that definition. The next part, being able to write and interpret chemical reactions for a system at equilibrium. So this would also be using that Kc expression. Here, taking a look and understanding shifts. So if you have a temperature change, you need to know whether you have an exo or endothermic reaction, so we know what way our reaction would move. Pressure and volume will only affect gases, and that has to have a different amount of moles on each side, and we can go from there. Concentration, for sure, we can just add or take out. And then lastly, how catalysts do not affect anything. You just get to equilibrium faster, but has no other change. Then you have your Kc value. We want to know the only thing that can express Kc or change Kc is temperature, but that's it. And if you do have your reverse reaction, you would just do 1 over the Kc value to know what the Kc reverse would be. Bronsted and Lowry, you know that if acids donate hydrogens, bases accept them. And we also can start to look at this a little bit more, knowing what side's going to be favored based on placement. So when you're predicting if your acid is higher than your base, then your products are favored. If your base is higher than your acid, your reactants are favored. And if you have anything strong, like a strong acid or a strong base, you're not in equilibrium. So you don't have a side being favored because you have 100% products. You need to be able to identify an acid base conjugate pair, and that is just the difference of one hydrogen. You're beside each other on the table, which would be your acids page. Knowing what a buffer is, how you can resist a change in pH. So if you had a small amount of a weak acid or a weak base and you add in a very strong acid, then it would react with the base part of the buffer. If you add in a very strong base, it would react with the acid part. And so it's just able to resist that change until it can't. So that's the beginning. We also want to be able to show those stages on a graph. And that's when your graph would be a bit flatter before the jump. Moving on from there, we also do need to know how to calculate all of that, which we would have calculated in Chem 20. So like pH, POH, hydronium, hydroxide. And we also want to know how to use these values, Kw, Ka, Kb, to figure out some of these if needed, if we have a weak acid or a weak base. So moving on from there, there's a little bit more here. For 11, it's knowing about our ice system. So if you had to set up an ice chart to figure out Kc or to figure out an unknown concentration at equilibrium, we're able to do that. So a little bit more here, and it has to do with your experiments and things that we can do here. The last thing I think I just add in here is just when you do have a titration to make your pH curve, that anytime you're taking a look at a pH curve, that the pH is always measured from the Erlenmeyer flask. So if your pH is starting lower, you know that it would be an acid. If it's starting up higher, near 14, you know it's going to be a base. And then when you are drawing it out, if it's monoproduct, meaning you just have one equivalence point, it's always going to look something like this. If it's diproduct, meaning you have more than one equivalence point, you would have something like that. So here would be 1, here would be 2, and we'd have some buffer regions if we had nothing strong happening. So I hope this helps. As always, if you stayed with me till the end, please subscribe. And if there's anything else I can do for you, let me know. And if you did stay this long and you're writing the diploma on Monday, I wish you very, very, very good luck on it. And I hope it all goes well. Thank you for watching.